The content of this presentation is for educational and informational purposes only and does not constitute professional engineering or architectural advice. The patterns and principles discussed are based on established literature and industry practices, but their application to specific real-world systems requires careful consideration of your unique context, constraints, and requirements. You should always consult with qualified professionals before making architectural decisions for production systems. Picture this. A brand new e-commerce site launches. It's beautiful. The marketing is perfect. On day one, a customer, let's call her Sarah, finds the exact pair of sneakers she's been looking for. She clicks buy now. The payment goes through. A thank you page appears. Success, right? Wrong. Days go by. No shipping notification. Sarah contacts customer support. The support agent pulls up her order. It says paid, but the status is stuck on awaiting shipment. The agent checks the warehouse system. There's no record of the order. He checks the inventory system. It still shows the sneakers in stock. The systems are lying. The payment system took the money, the order system recorded the sale, but the message to the warehouse to actually pack and ship the product vanished into thin air. Sarah is angry, the company has lost a customer, and a team of engineers is now frantically digging through logs, trying to figure out where the digital equivalent of a signed and sealed package just disappeared. This isn't a story about a junior developer making a typo. This is a story about a failure of communication, not between people but between software. And it happens every single day in thousands of companies, costing them millions, sometimes billions, in lost revenue, customer trust, and wasted engineering hours. The problem is that we build applications like isolated islands. The sales app is an island. The inventory app is an island. The shipping app is an island. And we try to connect them with flimsy, custom-built bridges. When one bridge breaks, the whole Rube Goldberg machine of a business grinds to a halt. But what if there was a better way? What if there was a set of proven, battle-tested blueprints for connecting these islands? A playbook used by companies like Amazon, Netflix, and Uber to handle billions of transactions flawlessly? There is. It's called Enterprise Integration Patterns. And over the next 10 parts, we are going to visually deconstruct this entire playbook. This isn't going to be a dry academic lecture. This is a visual guide for builders. By the end of this series, you won't just understand the jargon. You will have a completely new mental model for how to design software. You'll be able to look at a complex diagram of interconnected boxes and lines and immediately see the flow, diagnose the choke points, and design systems that are not just functional, but resilient, scalable, and elegant. You will learn the secret language that separates good engineers from great architects. So let's start with the most fundamental building block of this entire universe. It's not code. It's not a server. It's the message. Everything in a modern, distributed system boils down to sending messages. But what is a message? It's not just a string of text. A message is a self-contained packet of data, a little data envelope that's sent from one application to another. Think of it exactly like a letter you send through the postal service. A physical letter has two main parts: the envelope and the letter inside. A digital message is the same. It has a header and it has a body. The body is the payload. It's the what? It's the actual letter inside the envelope. In our e-commerce disaster, the body of the message might contain the order details. Sarah's name, her address, the product ID for the sneakers, the price she paid. It's the core piece of information we're trying to communicate. But the body alone isn't enough. You can't just drop a letter in a mailbox. You need an envelope with an address on it. That's the header. The header contains metadata. It's the data about the data. It's the to address, the from address, a timestamp, maybe a tracking number, or a priority level. The crucial thing here is that the system that transports the message, the mailman in our analogy, doesn't need to open the envelope and read the letter to know where it's going. It only needs to read the header. This is a profoundly important idea, the separation of the transport layer from the content. It's what allows our systems to be flexible. So, we have our message, our digital letter, neatly packaged with a header and a body. Now how do we send it? We can't just throw it into the void. We need a postal service. We need roads. In integration, we need a message channel. A message channel is the pipe, the conduit, through which messages travel from a sender to a receiver. It's the highway system for your data. And just like highways, there are different kinds of channels for different kinds of traffic. The two most important types you need to know are the point-to-point channel and the publish-subscribe channel. A point-to-point channel is the simplest. It's like sending a letter directly to a specific person. One sender, one receiver. When the order system sends a new order message, it sends it to a channel that is being listened to by one, and only one other system, the warehouse system. The message is consumed. It's gone. It's a direct, one-to-one conversation. This is perfect for commands. Pack this order. Charge this credit card. It's clear, direct, and unambiguous. But what if other parts of the business are also interested in that new order? The analytics team wants to update their sales dashboard. The marketing team wants to know what products are popular so they can run a new ad campaign. The customer service team wants a record of the order in case Sarah calls. Are we going to make the order system send a separate, direct message to each one of them? What happens when we add a new fraud detection system? Do we have to go back and change the code in the order system to send yet another message? This creates a brittle, tangled mess. Every time you add a new system, you have to modify the original sender. This is a recipe for disaster. This is where the second type of channel, the publish-subscribe channel, changes the game. Instead of a private letter, think of a publish-subscribe channel, or pub/sub for short, as a radio broadcast. The order system is the radio station. It doesn't send a message to a specific listener. It just publishes the order-placed event out onto a specific frequency, the channel. It shouts into the void, "Hey everyone! Order number 123 for a pair of sneakers was just placed." The radio station has no idea who is listening, doesn't care. Its only job is to broadcast the event. Now, any other application that is interested in that event can subscribe to that channel. They can tune their radios to that frequency. The analytics system tunes in, hears the message, and updates its dashboard. The marketing system tunes in, hears the message, and logs the product's popularity. The new fraud detection system can be added tomorrow, and all it has to do is tune into the same frequency. The original order system doesn't need to change at all. It doesn't even know the fraud system exists. This is the magic of decoupling. The publisher is completely disconnected from the subscribers. You can add or remove subscribers at will without ever touching the publisher. This single pattern is the foundation of modern, event-driven architectures that allow companies like Netflix to operate at a global scale. When you finish watching a show, a video watched event is published. One subscriber might update your continue watching list. Another might feed that data into the recommendation algorithm. A third might trigger a new episode available notification. All happening in parallel, all decoupled from the video player itself. So let's recap. We have messages, which are like letters with a header and a body. And we have message channels, the pipes they travel through. We have point-to-point channels for direct commands, and we have publish-subscribe channels for broadcasting events to anyone who's interested. This is the absolute bedrock. But it raises a critical question. We have the letter and we have the mail route. But what about the mailbox? What about the post office at the end of the line that actually receives the letter, opens it, and acts on it? And more importantly, in our story about Sarah's lost sneakers, what happens if the message is put on the channel, but the receiving system is down? Does the message just disappear forever? How do we build systems that can survive crashes and guarantee that every single critical message gets delivered no matter what? That is the role of the message endpoint. It's the smart device on the end of the pipe that ensures reliability, and it's the missing piece that would have saved Sarah's order. And that is exactly what we will break down in the next part. So let's rewind the clock on Sarah's order. The button was clicked, the data was sent, but somewhere in the digital void, the message was lost and her book never arrived. The problem wasn't the pipe. The messaging channel was fine. The problem was that the systems at either end were just shouting into the pipe, hoping for the best. There was no one there to catch the message, to sign for it, to make sure it was understood and acted upon. This is where the message endpoint comes in. It's not just part of the plumbing. It's the intelligent interface at the end of the line. To understand this, let's stop thinking about our systems as monolithic blocks of code. Instead, imagine each of our departments, ordering, inventory, and shipping, now has its own hyper-competent personal assistant. This assistant's entire job is to handle all incoming and outgoing messages for their department. This assistant is the message endpoint. Let's look at the inventory department's assistant first. His name is Iggy. When a message comes flying through that pneumatic tube from the ordering department, it doesn't just fall into a random bin. Iggy is there waiting. He catches it. This is the first and most crucial role of a message endpoint. It is a message consumer. It actively listens to a specific channel, waiting for a message to arrive. But Iggy doesn't just grab the capsule and walk away. The very first thing he does is send a tiny simple message back through the tube that says, "I got it." This is the concept of acknowledgement. It's the difference between sending a letter and getting a delivery confirmation signature. The ordering department's assistant now knows, with 100% certainty, that the message has been safely received. The responsibility has been transferred. Even if the entire inventory system crashes and burns 1 second later, it doesn't matter. Iggy has the message in his hand safe and sound. He'll hold on to it and deliver it to the inventory system as soon as it's back online. Right there, we've solved the problem of lost messages. Sarah's order is no longer lost in transit. It's guaranteed to be in Iggy's possession. But Iggy's job isn't done. He's not just a glorified mailman. His second task is to understand the message. He opens the capsule, pulls out the note, and reads it. The note might be written in a specific format, like a standardized order form. Let's say it's a JSON or XML file. Iggy knows how to read this format. He sees the book title, the quantity, Sarah's customer ID, and the order number. He's not just holding an envelope. He understands the intent of the message. The intent is, reserve 1 copy of the Midnight Labyrinth for this order. This is the processing part. The message endpoint acts as the bridge between the generic world of messaging and the specific world of the application it serves. Now for his third task, taking action. Iggy turns around and walks over to the giant, complicated machine that is the inventory system. He doesn't just throw the note at it. He knows exactly which buttons to press, which levers to pull. He interacts with the system's internal logic, telling it, "Hey, decrement the count for the Midnight Labyrinth by 1, and reserve this copy for order number 734. The inventory system does its job, and the book is now officially set aside for Sarah. The message endpoint translates the abstract request from the message into a concrete action within its own system. But the story doesn't end there. The book is reserved, great. But what about shipping? The shipping department needs to be told to actually box up the book and send it out. The inventory system itself doesn't know or care about shipping. Its job is just to track books on shelves. So Iggy, our inventory assistant, has one more job. After he gets confirmation from the inventory system that the book is reserved, he pulls out a new piece of paper. He writes a new message. This one says, "Order 734 is ready. Ship 1 copy of the Midnight Labyrinth to this address." He then walks over to a different pneumatic tube, the one that leads to the shipping department, and sends this new message on its way. In this moment, Iggy is no longer a message consumer. He has become a message producer. So, a message endpoint can be a listener, a producer, or both. It's the smart agent that allows a system to participate in a larger conversation without having to understand all the messy details of how that conversation works. Now let's replay Sarah's order one more time, with our new assistants in place. Sarah clicks buy. Instantly, the ordering department's assistant, let's call her Orla, crafts a perfect, standardized message containing all the order details. She places it in the channel to inventory and sends it. A moment later, Orla receives an acknowledgement. Got it, signed Iggy. Orla can now confidently update Sarah's screen to say, order processing. She has fulfilled her promise. Her job is done. She doesn't need to know what happens next. Over in inventory, Iggy takes the message. He reads it, turns to his system, and reserves the book. The system confirms. Then, Iggy writes his new message and sends it to the shipping department's channel. He gets an acknowledgement back from their assistant. Let's call him Skip. Iggy's job is now done. Finally, Skip, the shipping assistant, gets the message. He knows exactly what to do. He tells his shipping system to generate a label, get a box, and he sends a command to a warehouse robot to go pick the physical book off the shelf. Once the package is on the truck, Skip might even produce one final message, sending it to a notification system to email Sarah her tracking number. Look at the beauty of this. Each system only has to worry about its own job. The ordering system just makes orders. The inventory system just manages stock. The shipping system just ships packages. They are completely independent. This introduces one of the most powerful ideas in all of software architecture: decoupling. Because Orla, Iggy, and Skip are handling the communication, the underlying systems no longer need to know anything about each other. The ordering system could be a brand new piece of technology, while the inventory system could be a 30-year-old mainframe computer chugging away in a basement. It doesn't matter. As long as they're assistants, the message endpoints know how to talk to each other through the messaging system, the whole process works flawlessly. This means you can upgrade, replace, or take down one system for maintenance without the whole company grinding to a halt. If the inventory system is down for an hour to be rebooted, the order messages from Orla just start to pile up in the channel. Iggy is figuratively waiting outside the door. The moment the system is back online, he'll be there with his stack of messages, ready to process them in order. The business keeps running. The orders are not lost. Sarah's experience is seamless. That is the power of a simple pattern. A channel for the message to travel, and an endpoint to intelligently handle it on either side. It transforms a brittle, chaotic system of direct calls into a resilient, flexible, and scalable architecture. It allows different parts of a business to evolve independently, which is the key to building complex systems that can actually stand the test of time. We've solved reliability. We've solved the problem of systems being temporarily offline. We've made our entire operation more robust. But in describing our solution, I made a subtle and dangerous assumption. I said that Orla, Iggy, and Skip all understood the messages. Orla wrote the order on a specific form, and Iggy knew exactly how to read that form. But what happens when that's not the case? What happens when a company acquires another, and their systems speak completely different languages? What if Orla's order form is in English, but Iggy's ancient inventory system only understands German? Iggy can receive the message just fine, he can acknowledge it, but when he opens it up, it's complete gibberish to him. The message is delivered reliably, but it's useless. How do you bridge the communication gap between systems that were never designed to work together? You can't just tell the whole company to standardize overnight. You need a translator. And in the world of integration, that is exactly what we have. It's called a message translator. And it's one of the most fundamental, most critical patterns in the entire integration playbook. Think about it. When you have two systems, say a modern cloud-based sales platform and a 30-year-old mainframe that handles inventory, they don't just have different technologies. They have different worldviews. They represent data in completely different ways. The new sales system thinks of a customer as a rich JSON object, with nested fields for addresses, contact methods, and order history. It speaks the language of the modern web. The old mainframe, on the other hand, thinks of a customer as a single 200-character fixed-width line in a text file, where the first 30 characters are the last name, the next 30 are the first name, the next 5 are the zip code, and so on. It speaks a language from a different era. A message translator is the component that sits between them. Its sole purpose is to receive a message in one format and transform it into another format. It takes that elegant JSON object from the sales system and painstakingly flattens it, pads it with spaces, and truncates fields to fit the rigid structure the mainframe demands. And it does the reverse, taking the cryptic line of text from the mainframe and rehydrating it into a structured JSON object that other modern systems can understand. This sounds simple, but the implications are profound. Without the translator, these two systems could never communicate. The business would be stuck, unable to get real-time sales data into its core inventory system. But with the translator, the two systems can coexist, each operating in its own native language, completely unaware that a translation is even happening. The integration layer becomes an invisible, universal diplomat. But this raises a huge problem. If you have 10 different systems, do you need to write a translator between every single pair? System A to System B, A to C, A to D, then B to C, B to D, and so on? The number of translators you'd need to write would explode. For 10 systems, you'd need 90 translators to allow any system to talk to any other. It's a nightmare of complexity. It's unmanageable. This is where the architects of integration had a truly brilliant idea. They introduced the concept of a canonical data model. The word canonical just means a standard, accepted, or official version. Instead of every system learning every other system's language, what if everyone agreed to speak one common language? Imagine the United Nations. Instead of hiring translators for every possible language pair, a Finnish to Swahili translator, a Portuguese to Korean translator, they standardize on a few official languages. A diplomat from Finland speaks, a translator converts it to English, and then other translators convert that English version into Swahili, Portuguese, and Korean. The canonical data model is the English of our integration system. It's a common standardized format for the core business concepts, like customer, order, or product. We designed this ideal format once. It's not tied to any single application. It's the business's pure definition of what an order is. Now the process is much simpler. When the sales system sends its JSON order, it doesn't go directly to the mainframe. It first goes to a translator that converts the JSON into our standard, canonical order format. Then, another translator takes that canonical order and converts it into the fixed width format the mainframe understands. We've added an extra step, but we've slashed the complexity. For our 10 systems, we no longer need 90 translators. We just need one translator for each system to convert its local language to the canonical language, and one to convert from the canonical language back. That's only 20 translators in total. And if we add an 11th system, we just need to build 2 new translators for it, not 20 new ones. We've created a plug-and-play architecture. So now our messages are all speaking the same language. They're flowing through our system in a beautiful, standardized format. But where do they need to go? An order message doesn't need to go to every single system in the company. A new employee record from HR is irrelevant to the warehouse inventory system. We need a traffic cop, a mail sorter. We need a component that can look at a message and, based on certain rules, decide exactly where it should be sent. This is the message router. A router is a filter. It sits on a message channel and examines each message that passes through. Based on the message's contents or metadata, it directs the message down a specific path, while other messages continue on a different path, or are discarded entirely. The most common and powerful type is the content-based router. It makes its decision by looking inside the message itself. Let's go back to our e-commerce order, which is now in our beautiful canonical format. The router might look at a field called order_total. If that total is greater than $5,000, the router sends the message to a special channel for high-value order review, where it undergoes additional fraud checks. All other orders under $5,000 are sent down the standard fulfillment channel. Or maybe the router looks at the shipping_country field. If the country is USA, it goes to the domestic shipping system. If it's anything else, it's routed to the international shipping system, which has to handle customs declarations and duties. The business logic, the if this then that, is no longer locked away inside individual applications. It's right here, visible and configurable within the integration layer itself. This makes the entire enterprise more agile and easier to change. But what if a message needs to go to more than one place? When a new product is created in the catalog system, that information needs to go to the public website, the internal sales dashboard, and the marketing team's promotion engine all at the same time. For this, we use a pattern called the recipient list. The router inspects the message, sees it's a new product event, and consults a list of required destinations. It then creates a copy of the message for each recipient and sends them out on their respective channels. It's like sending a group email instead of a direct message. These routing patterns give us incredible control over the flow of information. But there's one more fundamental problem we have to solve. Sometimes a single large message is actually a collection of many smaller individual pieces of work. Think about an order that contains 10 different items. The warehouse doesn't process the order. It processes each line item on the order. Pick the book, pack the coffee maker, find the socks. Each is a discrete task. If we send the entire order to the fulfillment system as one giant message, we create a bottleneck. The system has to process all 10 items sequentially. And what happens if one item, say the coffee maker, is out of stock? Does the entire order fail? Do the other 9 items that are in stock just sit there waiting? This is inefficient and brittle. The solution is a pattern called the splitter. A splitter takes a single composite message and breaks it apart into a series of smaller, individual messages, each corresponding to a piece of the whole. It would take our one order message with 10 items and produce 10 separate, fulfill line item messages. Now, each of these 10 messages can be processed independently. We could even have 10 different warehouse workers or 10 different robotic arms process them all at the same time in parallel. It dramatically increases throughput, and it makes the system more resilient. If the coffee maker message fails because of a stock issue, the other 9 messages are unaffected. They continue on their journey, get picked, packed, and shipped. We can handle the one failure separately without stopping the whole train. So we've taken a message from its source, translated it into a common language, routed it intelligently based on its content, and even split it into smaller, more manageable pieces for efficient processing. We have mastered the art of taking things apart. But this creates a brand new and very difficult question. After we've split that order into 10 pieces, and they've all been processed separately, how do we know when the entire order is finished? How do we gather all those individual results back together to send a single, order shipped confirmation to the customer. We've mastered splitting things apart. But how on earth do we bring them back together? That process is one of the most powerful and most complex in all of enterprise integration. The answer lies in a set of patterns designed specifically for this challenge of reassembly. Think of it less like a chaotic scramble and more like a highly organized assembly plant. When you build a car, you don't just dump all the parts in a pile. The engine arrives, the chassis is ready, the doors are painted. Each component follows a process, waiting for the others at a specific station before being combined. Our messages need those same assembly stations. The first and most fundamental of these patterns is called the aggregator. The name says it all. The aggregator is a component that collects a series of related but separate messages and combines them into a single, complete message. It's the designated bin on our digital shipping dock. It has a label on it, say, Order 123, and it patiently waits. The message from the inventory system saying, Items picked arrives, and it goes into the bin. The message from the payment gateway saying Payment confirmed arrives, it goes into the bin too. The message from the shipping department saying Label printed arrives, and it joins the others. The aggregator just waits and it collects. Now, this sounds simple, but the devil is in the details, and this is where the genius of the pattern emerges. The aggregator has to answer 3 critical questions. If it can't, the entire system falls apart. First, how does it know which messages belong together? In a system processing thousands of orders a second, how does the payment confirmed message for order 123 not accidentally end up in the bin for order 456? The answer is a concept called a correlation identifier. This is a unique piece of data, a shared secret, that is present in all the messages that belong to the same group. In our case, the order ID, 123, is the perfect correlation identifier. Every message related to this specific order, whether it's from inventory, payment, or shipping, will carry this ID. The aggregator uses this ID like a key, ensuring only messages with the matching key get placed in the correct bin. Second, how does the aggregator know when it's finished? How does it know the collection is complete? Does it wait forever? No, it needs a completion condition. This is a rule that tells the aggregator, okay, you have everything you need. You can stop waiting now. This rule can be surprisingly sophisticated. A simple completion condition might be a fixed number of messages. For example, I know a complete order always consists of 3 messages: inventory, payment, and shipping. Once I have 3 messages with the same correlation ID, I'm done. But what if some orders require an extra step like a fraud check? A more robust completion condition might be based on the content of the messages themselves. Perhaps the final message in the sequence, let's say the one from the shipping department, contains a special marker, a flag in its data that says, last message. The aggregator's rule would then be, keep collecting messages until you receive one with the last message flag. This is far more flexible, and this leads to the third and perhaps most important question. What if a message never arrives? What if the payment system crashes and never sends its confirmation? Does our aggregator wait forever, holding on to the other 2 messages, clogging up the system with incomplete orders? This is a catastrophic failure scenario. To prevent this, the aggregator must use a timeout. This is a simple countdown clock. The moment the first message for order 123 arrives, a timer starts. Let's say 30 minutes. If the completion condition isn't met within those 30 minutes, the aggregator gives up. It declares the aggregation a failure, takes the partial collection of messages it did receive, and sends them to a special error handling process. An alert might be sent to a support team, or an automated process might try to requery the payment system. Without a timeout, a single failed service could bring your entire enterprise to a grinding halt. So the aggregator is our patient collector. It uses a correlation ID to group messages, a completion condition to know when it's done, and a timeout to prevent getting stuck forever. It's an incredibly powerful pattern for reassembling scattered data. But once the aggregator is finished, we have a new problem. It has successfully collected all the pieces. The bin for order 123 now contains 3 separate, raw messages. But that's all it is, a collection of raw materials. It's a pile of parts, not a finished product. We don't want to send the customer 3 cryptic internal system messages. We need to take that collection and forge it into one new beautiful message, the final order shipped confirmation. For this, we need a different pattern, one that often works hand in hand with the aggregator. It's called the composed message processor. If the aggregator is the collector, the composed message processor is the artist. Its job is to take the collection of messages and, following a set of rules, transform them into a single brand new message. It iterates through the incoming messages, plucking out specific pieces of data. It might take the customer's name from the payment message, the list of items from the inventory message, and the tracking number from the shipping message. It then weaves these disparate pieces of information together into a completely new structure, a clean, cohesive order-shipped email, ready to be sent to the customer. The original messages have served their purpose. They are the raw ingredients, and the composed message processor is the chef who creates the final dish. So you see the elegant dance between these two patterns. The aggregator gathers the raw data, and the composed message processor gives it meaning and purpose. But reassembly isn't just about collecting things that were split apart. Sometimes the problem is simpler. Things just arrive in the wrong order. Imagine you're processing financial transactions for a bank account. First, a message arrives for a $500 deposit. A few milliseconds later, a message arrives for a $100 withdrawal. The sequence is crucial. Deposit first, then withdraw. But thanks to the unpredictable nature of networks, what if the messages get swapped in transit? The withdrawal message arrives first. The system checks the account balance, sees insufficient funds, and incorrectly declines the transaction, maybe even charging the customer a fee. The deposit message arrives a moment later, but the damage is already done. To solve this, we use a pattern called the resequencer. It's a specialized, simpler version of the aggregator. Its only job is to ensure that messages are processed in the correct order. Each message in the sequence must have a number, a sequence identifier, that tells the resequencer its correct position. When messages arrive, the resequencer doesn't let them pass through immediately. It holds them. If message number 3 arrives, it waits. When message number 1 arrives, it's held. When message number 2 finally shows up, the resequencer sees it has 1, 2, and 3. It then releases them in the correct order. 1, then 2, then 3. It's a buffer that straightens out the chaos of the network, ensuring that order is imposed before the messages reach the next step in the process. Just like the aggregator, it also needs a timeout to handle cases where a message in the sequence is lost entirely and never arrives. These three patterns, the aggregator, the composed message processor, and the resequencer, form the backbone of message reassembly. They allow us to take a stream of scattered, disordered information and impose structure, meaning, and sequence upon it. They turn chaos into process. But as we talk about these patterns, you might notice a common and slightly terrifying thread connecting them. The aggregator has to remember the messages it has collected while it waits for more. The resequencer has to remember the out-of-order messages it's holding onto. They are not stateless like the simple filters or routers we discussed earlier. They are stateful. They have memory. And in the world of distributed systems, memory is both a superpower and a critical vulnerability. What happens if the aggregator service crashes in the middle of waiting for messages for 1,000 different orders? When it restarts, is all that information gone? Does it forget everything it was waiting for, leaving all those orders in a permanent state of limbo? Building a system that can reliably remember things, even in the face of crashes and network failures, is one of the hardest problems in software engineering. How do we build a memory that survives a disaster? The answer isn't about building a better brain. It's about building a better postal service. Think about it. When you make a phone call, you and the person you're calling have to be available at the exact same moment. If the line drops, the conversation is gone. It's fragile. It's synchronous. This is how our simple e-commerce system was working. The web store called the fulfillment service directly. If fulfillment was busy, restarting, or the network hiccup, the call failed, and the order was lost forever. But what if you send a letter instead? You write it, you put it in a mailbox, and you walk away. You trust the postal service to hold on to that letter, transport it, and deliver it. Even if the recipient isn't home, they'll hold it for them. The letter will wait. This is the core idea of messaging. Instead of applications talking directly to each other, they send messages through a central, reliable system, our digital post office. This simple shift in thinking from a phone call to a letter solves our memory problem. The messaging system itself becomes the memory. When our web store gets an order, it doesn't try to call the fulfillment service anymore. Instead, it carefully writes down all the order details into a package, a digital letter, and hands it off to the messaging system. The web store gets an instant confirmation. Message received. It can then immediately go back to serving other customers, confident that the order is safe. The messaging system, our trusted post office, now has the responsibility. It guarantees that this order letter will be delivered to the fulfillment service, even if it takes a few seconds or a few minutes because the service is down for a reboot. The memory of the order no longer lives in a fragile, temporary connection. It lives inside the robust infrastructure of the messaging system itself. This fundamental package of information is our first and most important pattern: the message. A message isn't just raw data. It's a structured, self-contained unit of communication. It's composed of two parts, just like a real letter: a header and a body. The body is the content, the letter itself. For our e-commerce site, the body would contain the order details: the customer's name, the products they bought, the shipping address. It's the what of the communication. The header, on the other hand, is the envelope. It contains all the metadata the messaging system needs to do its job. Who is this message for? Where did it come from? How should it be handled? Is it urgent? Does it expire? This is the how of the communication. By separating the what from the how, we create an incredibly flexible system. The applications handling the message only need to care about the body, the business data. The infrastructure, the digital postal workers, only care about the header, using it to route and manage the message without ever needing to open the envelope and look at the contents. So now we have these well-packaged digital letters, our messages. But where do we send them? You don't just hand a letter to a mail carrier and hope for the best. You put it into a specific mailbox, destined for a specific route. In our world, this is the message channel. A message channel is like a virtual pipeline. Senders put messages in one end, and receivers take them out the other. It's the street, the highway, the flight path that our messages travel along. The beautiful thing is, the application sending the message doesn't need to know anything about the application that will eventually receive it. It doesn't need its network address, its location, or even what programming language it's written in. All it needs to know is the name of the channel, the address on the mailbox. This creates a profound separation, a decoupling between our systems. They can evolve independently, be moved, be updated, and as long as they know which channels to listen to, the whole system keeps working. Now, not all mail delivery is the same. If you send a letter to your friend, you expect it to go to one and only one person. This is our next pattern: the point-to-point channel. It ensures that for any given message sent to the channel, only one receiver will consume it. It's a direct, one-to-one communication, even though it's asynchronous. When our web store creates a new order message, it sends it to the new orders channel. The fulfillment service is listening to that channel. It sees the message, picks it up, and starts processing the order. If we had two fulfillment servers running for redundancy, the point-to-point channel would still ensure that only one of them gets that specific order. The message is consumed, gone from the channel, preventing the customer from being charged twice or having their order shipped twice. It's a work queue, a digital assembly line where each task is picked up by the next available worker. But what if the information isn't for just one recipient? What if it's a public announcement? Imagine our marketing team runs a flash sale, and the price of a popular product is updated. The main website needs to show the new price. The inventory system needs to be aware of the promotion. The analytics service needs to track the sales performance. Using a point-to-point channel here would be a nightmare. We'd have to send a separate, identical message to 3 different channels. If a fourth system, say a social media bot, needs to know about price drops, we'd have to go back and change the original sender's code to send yet another message. This is tightly coupled and brittle. This is where a different kind of delivery shines. This is the publish-subscribe channel. Think of it not as sending a personal letter, but as publishing a newspaper. The publisher prints the news and throws it on the newsstand. They have no idea who will read it, nor do they care. Any number of people can subscribe, pick up a copy, and read the same story. The publisher's job is done the moment the paper is printed. In our system, the pricing service publishes a single message to a product price updates channel. The message says, product SKU 123 is now $19.99. The website, inventory system, and analytics service have all subscribed to this channel. They each receive their own copy of the message and can react independently. The website updates its display. The inventory system flags the item for a potential surge in demand. The analytics service starts a new data gathering session. If we want to add that social media bot later, it simply subscribes to the channel. No changes are needed to the pricing service. It just keeps publishing its news, blissfully unaware of its ever-growing audience. This is decoupling at its most powerful. allowing systems to be truly independent and scalable. It enables an event-driven architecture, where systems react to events happening elsewhere, creating a dynamic and resilient enterprise. We've built a memory. We've replaced fragile phone calls with a robust, reliable postal service. We've defined our packages of information as messages and our delivery routes as channels. We've seen how to send a message to a single recipient with a point-to-point channel, and how to broadcast it to the world with a publish-subscribe channel. Our systems are now decoupled, reliable, and asynchronous. But a new problem emerges. What good is a perfect postal service if the recipient's mailbox is overflowing, with letters spilling onto the street? What happens when the fulfillment service, our receiver, can't keep up with the flood of orders coming down the channel? The answer is as simple as it is catastrophic. The system breaks. Not in a slow, graceful way, but in a cascading, spectacular failure. The fulfillment service's internal memory overflows. The server crashes. It reboots, tries to grab the first order from the channel again, and immediately crashes again. It's trapped in a death loop. Meanwhile, the e-commerce site, blissfully unaware, keeps piling on more orders. Customers get error messages. Orders are lost. The business grinds to a halt. This isn't a hypothetical problem. This is one of the most common failure modes in distributed systems. It's the classic fast producer, slow consumer problem. Our sender is a fire hose, and our receiver is trying to drink from it with a tiny straw. The channel, our message queue, acts as a buffer, but a buffer can only hold so much. Eventually, it overflows or the consumer simply chokes. So how do we fix this? The first, most intuitive answer isn't a complex algorithm. It's common sense. If one person packing boxes is overwhelmed by the sheer volume of orders coming down the conveyor belt, what do? You hire more packers. This is the essence of the competing consumers pattern. It is, without a doubt, one of the most powerful and fundamental patterns in all of enterprise integration. Instead of having one instance of our fulfillment application connected to the order channel, we run multiple instances. 2, 5, 100, it doesn't matter. They are all identical. They all connect to the exact same message channel. And they all compete to pull the next message off the queue. Think of our conveyor belt of orders. Now, instead of one packer, we have a whole team lined up. When an order comes down the belt, the first available packer grabs it and gets to work. While they're busy, the next order comes, and a different packer grabs that one. Suddenly, we're not processing one order at a time. We're processing many orders in parallel. We've scaled our capacity to meet the demand. If the e-commerce site has a flash sale and order volume triples, we can simply spin up more instances of our fulfillment service, hire more packers for the day, and the system doesn't even break a sweat. But this raises a critical question. If all these consumers are connected to the same channel, how do we prevent two of them from grabbing the same message? How do we stop two different packers from grabbing the same order slip and shipping the same product to the same customer twice? This is where the magic of the messaging system itself comes into play, through a mechanism called a message dispatcher. The dispatcher is like the foreman at the fulfillment center. Its one job is to stand at the head of the conveyor belt and hand each order to exactly one, and only one, available packer. The messaging queue guarantees that once a message is delivered to a consumer, it is locked and invisible to all the other competing consumers. It will not be delivered again unless the first consumer fails to process it, and the message is returned to the queue. This atomic delivery is the cornerstone that makes the competing consumers pattern possible. It allows for incredible scalability and also high availability. If one of our fulfillment service instances crashes, if one of our packers suddenly gets sick and goes home, the foreman simply stops handing them orders. The other packers just keep working, picking up the slack. The system is resilient. Okay, so we've solved the speed problem. We can now process orders as fast as they come in. But a new, more subtle challenge appears. In our simple first in, first out queue, every order is treated equally. But in the real world, are they? What about the customer who paid an extra $20 for overnight shipping? Their order is sitting in the queue behind thousands of standard shipping orders that came in during the flash sale. They're going to be furious. We need a way for a consumer to be more discerning. We need a selective consumer. This pattern allows a consumer to receive only the messages that match a specific set of criteria. Here's how it works. When the e-commerce site creates the order message, it doesn't just put the order details in the body of the message. It also adds metadata, or what are often called headers or properties. Think of it like putting a big, red priority sticker on the outside of the envelope. We could add a property like shipping_method, express, or customer_platinum. Now we can create a special consumer. This consumer connects to the same order queue, but it tells the message dispatcher, "Hey, I'm only interested in messages that have the priority sticker on them." The dispatcher, being very helpful, will now let this special consumer peek into the queue and pull out only the express orders, even if they're buried behind thousands of others. We can have a dedicated pool of competing consumers that only handle express orders, ensuring they are processed immediately, while another, larger pool of consumers handles the standard orders. The selective consumer pattern gives us the power to prioritize and filter, bringing a new level of intelligence to our message processing. We've figured out who processes the messages, our team of competing, sometimes selective consumers. But there's one more fundamental question to answer. How does a consumer actually get a message from the channel? There are two primary models for this, and the choice between them has massive implications for the efficiency and responsiveness of your system. The first model is the polling consumer. A polling consumer is proactive but not in a good way. It's like an impatient child on a road trip, constantly asking, "Are we there yet?" The consumer is locked in a loop. Ask the channel for a message. "Did I get one? No. Wait 1 second. Ask the channel for a message. Did I get one? No. Wait 1 second. Ask again." When there are always messages waiting in the queue, this works okay. But what if orders are infrequent? What if we only get an order every few minutes? Our polling consumer is spending almost all of its time and CPU cycles asking for messages that aren't there. It's wasting resources and it introduces latency. If we set the polling interval to 1 second, then on average, a new message will sit in the queue for half a second before it's even picked up. There has to be a better way. And there is. It's the event-driven consumer, also known as an asynchronous receiver. Instead of the consumer constantly asking the channel for work, the event-driven consumer simply tells the channel, "Hey, I'm here and I'm ready. Let me know when a message arrives." It then sits back and waits. It consumes virtually zero resources while it's idle. The moment a new message hits the queue, the messaging system itself proactively pushes the message to the waiting consumer. An event is fired, the consumer wakes up, processes the message, and then tells the channel, "Okay, I'm ready for the next one." This is vastly more efficient. There are no wasted CPU cycles. And it's incredibly fast. The latency between a message arriving and processing beginning is measured in milliseconds. This push-based, event-driven model is the foundation of modern, reactive, real-time systems. It's the difference between constantly refreshing a web page to see if you got an email and getting an instant push notification on your phone the moment it arrives. So let's take a step back and see what we've built. We started with a single, overwhelmed receiver on the verge of collapse. Now, by applying these endpoint patterns, we have a fleet of competing consumers, allowing us to scale horizontally to meet any demand. We have selective consumers that can prioritize high-value messages, ensuring critical tasks are handled immediately. And we're using the hyper-efficient event-driven consumer model, building a system that is both powerful and resource-friendly. We have tamed the flood. Our fulfillment center is a model of efficiency, but in our quest for speed and scale, we've overlooked a dark and dangerous possibility. All of this assumes that the messages themselves are perfect. What happens when a message is poison? What happens if a corrupt, malformed order message gets into our queue? A message that causes our application to crash every single time it tries to process it. One of our event-driven consumers will grab it instantly. It will try to process it and it will crash. The message, unacknowledged, will return to the front of the queue. Another consumer, now free, will immediately grab that same poison pill message. It will try, it will crash, and the message will go back. Do you see the pattern? How do you stop a single bad message from creating a chain reaction that brings your entire fleet of consumers to a grinding, permanent halt? The answer is a pattern with a name that sounds grim, but is actually a lifesaver. It's called the dead letter channel. Think about it in terms of physical mail. Imagine a mail carrier trying to deliver a package. The address is smudged, it's unreadable. The carrier tries their best, maybe they ask a neighbor, but they just can't deliver it. What happens next? Does the carrier put the package back in the truck, only to pull it out again tomorrow and try the exact same failed delivery day after day forever? Of course not. That would be insane. It would grind the entire mail system to a halt. Instead, the package is declared undeliverable. It's taken out of the main delivery flow and sent to a special facility. In the U.S. Postal Service, this is the Mail Recovery Center. a centralized place where they can investigate these problem packages without holding up the millions of other packages that are perfectly fine. The dead letter channel is the digital equivalent of that mail recovery center. Here's how it works. Our consumer, the one that keeps crashing, makes a new agreement with the message broker. It says, I will attempt to process any given message a certain number of times. Let's say 3 times. This is our retry policy. So the poison pill message arrives. The consumer tries to process it, fails and crashes. The message goes back to the queue. The consumer restarts, picks up the very same message again. This is attempt number 2. Fails again. Back to the queue. Picks it up one last time. This is attempt number 3, the final try. Fails predictably. But this time something different happens. Because the retry limit has been reached, the consumer now treats the message differently. Instead of just putting it back at the head of the line, it performs a special action. It moves the message from the primary, active queue to a completely separate, pre-configured queue. The dead letter channel, or DLQ for short. And just like that, the problem is solved. The poison pill is no longer in the main channel. It's been safely isolated. The next message in the queue, a perfectly healthy one, can now be picked up and processed successfully. The logjam is broken. The entire system breathes a collective sigh of relief and gets back to work. This pattern is fundamentally about resilience. It's about building systems that can automatically heal themselves from certain types of failures. A single piece of bad data should never be allowed to cause a catastrophic system-wide outage. The dead letter channel acts as a safety valve, preventing this precise scenario. But its value goes far beyond just preventing crashes. The DLQ is an incredible diagnostic tool. It's not a message graveyard. It's an investigation room. Every message that ends up in the DLQ is a breadcrumb, a clue pointing to a problem in your system. It could be a bug in your code, malformed data from a client, or an unexpected change in an external service you depend on. By monitoring the dead letter channel, you gain immense insight. You don't have to go digging through terabytes of logs to find out why things are failing. The failures come to you neatly collected in one place. You can set up alerts so that whenever a message lands in the DLQ, your engineering team is immediately notified. They can then inspect the message, its headers, its payload, and understand exactly what went wrong and why. Let's go back to our e-commerce example. An order-placed message contains a list of product IDs. One of our consumers, the inventory service, is responsible for processing this message to decrement the stock count for each product. Now, imagine an order comes through for a product ID that simply doesn't exist. Maybe the product was deleted from the database a split second after the customer added it to their cart. The inventory service picks up the message. It tries to look up product ID 9-8-7-6-5 in the database. The database says, not found. The service, programmed to believe the product must exist, throws an error and crashes. The message goes back to the queue. It retries. Same result. Fails again. On the third failure, instead of poisoning the well, the inventory service moves the faulty order message to the inventory service fail queue. Instantly, an alert fires in the engineering team's Slack channel. New message in inventory service fail queue. A developer clicks the link. They look at the message payload. They see the non-existent product ID. They can immediately diagnose the root cause. Now they have options. They can write a small script to fix the data and resubmit the message to the main queue. Or they can trigger a process to cancel that part of the order and notify the customer. The most important part? While all of this investigation was happening, 10,000 other valid orders were processed without a single hiccup. The one bad order didn't stop the entire business. That is the power of the dead letter channel. Now, for this to work robustly, the act of moving the message must be atomic. This is critical. The consumer can't just delete the message from the main queue and then hope it successfully adds it to the DLQ. What if it crashes between those two steps? The message would be lost forever. This is where the transactional client pattern we discussed earlier becomes a powerful ally. The consumer starts a transaction. Within that single transaction, it does two things. It acknowledges or deletes the message from the source queue, and it sends the message to the dead letter channel. It then commits the transaction. Both actions succeed or neither does. If anything goes wrong, the transaction is rolled back, and the message is safely returned to the source queue for another attempt. This guarantees that no message is ever lost in transit to the DLQ. So we have our solution. A robust, self-healing system that isolates poison pills and gives us a clear, actionable list of everything that's gone wrong. It seems like we've built an impenetrable fortress. Our queues are safe, our consumers are resilient. But there's a subtle and terrifying assumption we've been making this whole time. We've assumed that the problem is always with the message. We designed the dead letter channel to handle a poison pill. But what if the problem isn't the message? What if the consumer is the one that's been poisoned? Imagine we deploy a new version of our inventory service. It has a subtle bug. It can no longer connect to the database because of an expired certificate. Now it doesn't matter what message it receives. Whether the product ID is valid or not, it will fail every single time it tries to connect to the database. The first message comes in. It's a perfectly valid order. The consumer tries, fails to connect to the database. Retries, fails. Third try, fails. It dutifully moves the message to the dead letter channel. Then the next message comes in. It's also perfectly valid. The consumer tries, fails, retries, fails, third try, fails. It moves this message to the DL queue as well. Do you see what's happening? Our consumer has gone rogue. It's now treating every single message as a poison pill. Our dead letter channel, designed to be a small investigation room for rare exceptions, is now being flooded with every single order our company receives. The main queue is being processed, but nothing is actually succeeding. Everything is just being shunted into the failure queue. We've stopped the system from crashing, but we've created a silent, massive failure. The dead letter channel protected the queue from a bad message. But how do we protect the entire system from a bad consumer? This is a subtle but catastrophic shift. The poison message was an external threat, an invader we could isolate. But what if the problem is internal? What if one of our own services has gone rogue? A consumer that continuously pulls a message from the queue, tries to process it, fails, and puts it right back on the queue, only to immediately grab it again. It gets stuck in a frantic, useless loop, consuming CPU cycles, flooding logs with errors, and starving all the other healthy consumers who are waiting for their turn. This isn't a poison message anymore. This is a poison pill. The message itself is fine, but the consumer is choking on it, and it's threatening to take down the entire system through sheer exhaustion. The dead letter channel doesn't help here, because the failure isn't in the message, it's in the processing. The consumer is the source of the problem. We need a way to quarantine the consumer itself. We need a pattern that can detect when a component is sick and temporarily isolate it from the rest of the system to prevent the infection from spreading. This is the job of one of the most famous and critical patterns in modern systems architecture, the circuit breaker. And yes, it's named after exactly what you think it is. The circuit breaker in your house. What does it do? When it detects a dangerous overload of current, like when you plug in a faulty toaster, it trips. It physically breaks the connection, stopping the flow of electricity before your house burns down. It sacrifices the function of one outlet to save the entire building. The software circuit breaker pattern does the exact same thing for our services. It wraps a protective layer around a dangerous operation, like a call to another service or a database, and it watches for failures. To understand how it works, you have to visualize it in one of three states: closed, open, or half open. Let's start with the normal happy state. Closed. When the circuit is closed, it means the connection is complete. Requests are flowing through it to the consumer, just like electricity flowing to your toaster. In this state, the circuit breaker is just passively observing. It's counting. Specifically, it's counting failures. Maybe it's tracking the number of exceptions, or how many times a request times out. You can figure what a failure means. As long as everything is working, the circuit stays closed. But then the consumer starts to fail. The database it relies on goes offline. A bug is deployed. It starts throwing exceptions for every single message it tries to process. The circuit breaker, which has been quietly counting, sees the failure rate spike past a configured threshold. Maybe it's 5 failures in a row, or 50% of requests failing over a 30-second window. The moment that threshold is crossed, the breaker trips. It moves into the open state. This is the crucial system-saving moment. When the circuit is open, the connection is broken. Any new request that arrives at the circuit breaker is immediately rejected. It doesn't even try to call the failing consumer. Just fails fast. It returns an error straight away, without wasting a single millisecond or CPU cycle, trying to contact a service it already knows is unhealthy. This is profoundly important. First, it protects the producer. The application that's sending the messages isn't stuck waiting for a response from a dead service. It gets an immediate error and can move on. Second, and this is the most critical part, it protects the failing consumer itself. By cutting off the flow of requests, We're giving the sick service breathing room. We're taking it off the ventilator. If it crashed because it was overloaded, this pause gives it time to restart, to release resources, to recover. We've stopped hammering a service that's already down. So the circuit is open. The sick patient is resting. But for how long? We can't just leave it isolated forever. We need to know if it's recovered. This is where the third state comes in, half open. After a configured timeout period, say 60 seconds, the circuit breaker decides to test the waters. It moves from the open state into the half-open state. It's cautiously optimistic. In this state, it will allow a single trial request to pass through to the consumer. Just one. This single request is the canary in the coal mine. One of two things will happen. If that trial request succeeds, the circuit breaker assumes the consumer has recovered. It snaps back to the closed state, and requests start flowing normally again. The crisis is over. The system has healed itself automatically with no human intervention. But if that single trial request fails, the circuit breaker assumes the consumer is still sick. It immediately trips back to the open state, breaking the connection again, and starts the timeout timer all over. It will wait another 60 seconds before it even thinks about trying again. Let's map this back to our poison pill problem. We have a consumer that's stuck in a death loop, failing to process a message over and over. We wrap its processing logic in a circuit breaker. The first few attempts fail. The breaker is in the closed state, but it's counting. 1 failure, 2, 3, 4, 5. The threshold is hit. Click. The breaker trips to the open state. Now the message queue tries to send the next message to the consumer. But the circuit breaker is in the way. It doesn't even let the call happen. It immediately tells the queue, "Nope, service is unavailable. The message is not consumed. Stay safely in the queue." The rogue consumer is now silent. It's not spinning its wheels, it's not thrashing the CPU, it's not flooding the logs. It's quarantined. The rest of the system breathes a sigh of relief. Other, healthy consumers can now get messages from the queue and do their work. The system remains stable. After the timeout, the breaker moves to half open. It lets one message through. If the underlying problem was temporary, maybe the database it was talking to just needed a moment to restart. The processing might succeed. If it does, the breaker closes and the consumer gets back to work. If it fails again, the breaker snaps open, re-quarantining the consumer. The beauty of this is that it's an automatic, self-regulating fuse that protects your entire architecture from the blast radius of a single failing component. But using a circuit breaker effectively requires some careful thought. You have to decide what counts as a failure. Is a 404 not found error failure? Probably not, that's a normal response. Is a 503 service unavailable error failure? Absolutely. Is a request that takes more than 5 seconds a failure? Could be. This configuration is key to making the pattern work for your specific needs. You also have to set the right thresholds. If your failure threshold is too low, your breaker will trip all the time from normal transient network hiccups. You'll have an overly sensitive, flaky system. If your threshold is too high, it might take too long to trip, and the failing consumer could do serious damage before it's finally isolated. And the timeout, the time spent in the open state, is a delicate balance. Too short, and you don't give the service enough time to recover. Too long, and your service is offline for longer than it needs to be. The circuit breaker pattern masterfully solves the problem of a failing consumer. Stops the bleeding. Quarantines the problem. It prevents a local failure from causing a system-wide catastrophic cascade. But it creates a new, more subtle problem. When the circuit is open, it's rejecting requests. It's failing fast. From the perspective of the original producer, or even a human user, the action they tried to perform just failed. Instantly. We've protected the system's health, which is the top priority. But what about the user's experience? What about the work that was supposed to get done? Just telling the user sorry, try again later isn't always good enough. We've built a robust system, but is it a resilient one? How can we handle these failures more gracefully? Instead of just failing, could we offer a different, perhaps degraded experience? Could we provide some default data? Or maybe cue the work to be tried again later automatically? We've stopped the house from burning down. Now, how do we make it livable, even when one of the rooms is out of commission? This leads us to one of the most important concepts in modern systems design: graceful degradation. The goal isn't just to fail. It's to fail well. To fail in a way that the user barely notices, or at the very least isn't completely blocked. And the simplest, most powerful pattern for this is the fallback. If the kitchen is out of commission, you can't cook that 5-course meal. But you can order a pizza. The fallback is your pizza delivery number on speed dial. When a service call fails, it times out, it returns an error. Instead of letting that error cascade through the system and blow up in the user's face, a fallback component kicks in. It provides an alternative response. Maybe your fancy, AI-powered recommendation engine is down. The fallback doesn't just show an empty space. It returns a precompiled list of top 10 bestsellers. Is it personalized? No. Is it better than a giant error message? Absolutely. The user can still browse and buy. The experience is degraded but not destroyed. Or imagine a weather widget that can't reach the live weather service. A fallback could return the last known forecast with a small note, updated 30 minutes ago. Again, it's not perfect, but it's 1,000 times better than a broken component. The fallback is the ultimate pragmatist. It accepts that failure is inevitable and plans for it, ensuring the system can always put its best available foot forward, even if it's a little scuffed. A close cousin to the fallback is another pattern you're already familiar with. Even if you don't know its name, the cache. If you can't cook a fresh meal because the kitchen is closed, what's your next best option? Eating the leftovers you pre-made and stored in the fridge. That's a cache. In system design, a cache is a high-speed data storage layer that holds a copy of frequently accessed data. When a request comes in for, say, a user's profile information, the system first checks the superfast cache. If the data is there, a cache hit, it returns it immediately without ever bothering the main, slower database or user service. This makes everything feel incredibly snappy. But here's where it becomes a resilience pattern. What happens if that main user service goes down? The one we put a circuit breaker on? Well, the cache is still running. It has a slightly older or stale copy of the user's profile. When the request comes in, the application can be configured to say, the main service is down, but I have this data from 5 minutes ago. It's good enough. We can serve the user's name, their profile picture, their basic settings, all from the cache. The core functionality of the site continues to work. The user might not even notice the outage. This is the trade-off of caching. You sacrifice perfect, up-to-the-second data freshness for a massive gain in speed and availability. For a vast number of applications, serving data that's a few seconds or even a few minutes old is an acceptable price to pay for a system that feels unbreakable. So, with circuit breakers, fallbacks, and caching, we've built a pretty sturdy house. It can handle a room going out of commission. But what happens when the problem isn't a single broken room, but a massive crowd of people trying to get into the house all at once? A sudden, overwhelming spike in traffic. This is where we shift from being reactive to being proactive. How do we design the system to handle immense pressure without collapsing? The first tool for this is throttling. Think of a bouncer at the hottest new nightclub in town. There's a line of 1,000 people wrapping around the block. If the bouncer just opened the doors and let everyone rush in, the club would be instantly overwhelmed. It would be chaotic, dangerous, and nobody would have a good time. So what does the bouncer do? He throttles the entrance. He lets in 5 people, waits a minute, lets in 5 more. He controls the rate. In our systems, a throttling pattern does the exact same thing. It limits the number of requests a service will accept in a given window of time. An API might be configured to only accept 100 requests per second from a single user. If that user sends 101 requests, the last one gets an immediate 429 too many requests error. This is a crucial protective measure. It prevents a single misbehaving client or a sudden viral surge from overwhelming a downstream service and causing a cascading failure. It's the system saying, I can only handle so much at once. Get in line and wait your turn. But just telling clients to try again later can be crude. A more elegant solution is to actually create a line. This brings us to the queue-based load leveling pattern. Instead of having clients call our service directly, we put a message queue in front of it. Remember our post office from earlier? It's back, but this time its job is to manage crowds. All incoming requests are sent as messages to the queue. The queue is like that velvet rope line outside the nightclub. It can absorb a massive sudden burst of messages, thousands of them in a second, and hold them safely. Meanwhile, our service, the nightclub, works at its own sustainable pace. It pulls one message from the queue, processes it, then pulls the next one. It never gets overwhelmed. It doesn't matter if there's a flash mob of 1 million requests. The service just keeps working through the line one at a time. This pattern is a game changer. It decouples the producer of work from the consumer. The client that sends the request gets an immediate, Okay, I've got it response from the queue and can move on. It doesn't have to wait for the work to actually be finished. This makes the front end of your system feel incredibly responsive, while the back end can process the work steadily and reliably, ensuring stability even under the most extreme load spikes. Now, as we use these queues to manage load, another problem can emerge. What if the messages themselves are the problem? Imagine you're not just sending postcards through your post office, but someone is trying to mail a grand piano. A single massive message can clog the pipes. It consumes a huge amount of memory and network bandwidth, slowing everything down for everyone else. To solve this, we use a wonderfully clever pattern called the claim check. Think about checking a heavy winter coat at a theater. You don't carry the bulky coat around with you to your seat. You hand it to an attendant and they give you a small lightweight ticket, a claim check. When you want your coat back, you just present the ticket. The claim check pattern does exactly this with large messages. Before sending the message, a component first takes the large payload, the coat, and stores it in an external shared storage like a cloud blob store or a database. It then gets back a reference, a simple ID or URL, which is the claim check. Now it sends a tiny message through the queue containing only this claim check. The message flies through the system. It's small, it's fast. When the final consumer receives this tiny message, it reads the claim check, goes to the shared storage, and retrieves the full heavy payload to do its work. This is brilliant. It keeps your main messaging infrastructure lean and fast, optimized for moving small pointers around, not giant blobs of data. It prevents a single large message from causing system-wide slowdowns, making the entire integration more robust and performant. With these patterns, we've built a system that is not only resilient to failure but also to overwhelming success. It can degrade gracefully with fallbacks and caches. It can protect itself from massive traffic spikes using throttling and load leveling queues. And it can efficiently handle huge payloads with the claim check. We've engineered a truly remarkable distributed machine. Messages flow, services collaborate, errors are handled, and pressure is managed. But this raises one final critical question. In this complex city of interconnected components with messages zipping around like anonymous couriers, how do we actually know what's going on? When a user's request fails, how do we trace its entire journey through 5 different services to find out where things went wrong? We've built a powerful engine, but the hood is welded shut. We're flying blind. How do we give our system eyes and ears? How do we achieve true observability? The answer lies in a final crucial category of patterns: system management patterns. These aren't about processing business data. They're about managing the system itself. They are the instruments in our cockpit, the gauges on our engine, the nervous system that gives our architecture awareness. The first and most fundamental pattern is the correlation identifier. Think about it like this. When you order a package online, you get a tracking number. That number is unique to your order. It doesn't matter if it goes from a warehouse in California, to a sorting facility in Chicago, to a delivery truck in New York. At any point, you can use that single number to find out exactly where your package is. The tracking number is the correlation identifier. In our systems, when a new request comes in, say an order is placed, we generate a unique ID, a request ID, or correlation ID. We then attach this ID to the very first message. And here's the critical part. Every single service that touches this message, or creates a new message as a result of this one, must copy that same correlation ID onto the new message. The inventory service gets the order, checks the stock, and sends a stock reserved message. That message has the original correlation ID. The payment gateway processes the payment and emits a payment successful event. It has the same ID. The shipping service, the notification service, all of them propagate this one single unifying identifier. Now, when a customer calls and says their order from 3 days ago hasn't shipped, we don't have to guess. We don't have to look through the logs of 5 different services, trying to piece together a timeline based on timestamps and customer names. No. We ask for the order number, we find the correlation ID, and we plug that ID into our central logging system. Instantly, we see the entire story. We see the request enter the system. We see it hit the order service. We see it go to inventory. We see the payment succeed. And then, we see it never reach the shipping service. The log trail just stops. We've found the problem in seconds, not hours. The correlation identifier is the single red thread that lets us trace one specific transaction through the most complex, distributed maze. It turns our welded shut hood into a glass one. But what if we want more detail? What if we want to know the exact path a message took, not just that the messages are related? For For that, we use the message history pattern. Imagine our message isn't just carrying a tracking number, but an actual travel log like a passport. Every time it enters a new service, that service acts as a border agent. It takes out a stamp and adds an entry to the message's history. Arrived at inventory service, 10 hours 32 minutes and 15 seconds. Departed at 10 hours 32 minutes and 16 seconds. Then it passes the message with its newly updated passport to the next stop. When the message finally reaches its destination, we have a complete, ordered list of every single component it passed through and when. This is incredibly powerful for debugging complex routing logic. Maybe a message is being processed twice because a router is configured incorrectly. The message history will show it plain as day. Visited payment gateway. Visited shipping service. Visited payment gateway again. It's an audit trail baked directly into the message itself. Now we can see what's happening. But how do we know our system is healthy right now, before a customer is even impacted? We can't just wait for an error to happen. We need to be proactive. This is where the test message pattern comes in. A test message is a synthetic, canary in the coal mine request. We craft a special message that looks just like a real one. Maybe an order for a fake product to a test user account, but it's flagged internally as a test. We then inject this message into our system at the very beginning of the pipeline and wait for it to come out the other end. We can have a component at the end that specifically listens for these test messages. If it receives the message within an expected time frame, it knows the entire path is healthy. The pipes are clear. But if the message doesn't show up, an alarm bell rings. The canary has stopped singing. And because we know the expected path, we know exactly which part of our system has failed. We can fix the problem before a single real customer order is lost. It's a live end-to-end health check of your entire integration architecture. So we can see, we can audit, and we can proactively test. We have observability, but what about control? What happens when we need to actively manage the components in our running system without taking everything down for a deployment? This is the job of the control bus. Think of your messaging channels, your queues and topics, as the highways for your business data. Orders, payments, and notifications are the cars and trucks, all flowing to get their job done. The control bus is a completely separate, special-purpose highway. It doesn't carry business data. It carries commands. It's the private road that only system administrators can use. Through the control bus, we can send command messages to any component in our system. We could send a message to the shipping service that says, "Pause all message processing." Maybe the physical warehouse is having an emergency. The service receives this command, stops pulling from its queue, and waits for a resume command. Or maybe we're debugging a tricky issue in the payment gateway. We can send a command, "Set your logging level to debug." The component changes its configuration on the fly, starts spitting out incredibly detailed logs, and when we're done, we send another command, "Set logging level back to info." No restart, no deployment, just pure dynamic runtime control. The control bus is the command and control center for our entire distributed fleet. And with that, our journey is complete. Look at what we've built. We didn't just learn a list of patterns. We assembled a universe. We started with the fundamental particles, messages, the carriers of information. We connected them with channels, the pathways of communication. We learned the art of routing, how to direct messages with content-based routers, split them with splitters, and merge them back together with aggregators. We learned how to translate between different worlds using transformers and normalizers, ensuring every component could speak a common language. We built sophisticated process pipelines, chaining services together like a well-oiled assembly line. We tackled the challenge of long-running, stateful processes with the Saga pattern, ensuring our business transactions were either fully completed or fully undone, never left in a broken state. We made our system tough and resilient, using patterns like dead letter channels to handle failure gracefully and idempotent receivers to protect against duplicate messages. And finally, today we gave our system a consciousness. With correlation IDs, message histories, test messages, and the control bus, we gave it the ability to be observed, understood, and controlled. These patterns are more than just technical diagrams. They are a language, a shared vocabulary for designing and building complex systems that actually work. They allow us to tame complexity, to break down monumental challenges into small, manageable, and solvable problems. When you look at a massive interconnected system, you won't see a terrifying, unknowable monolith anymore. You'll see the patterns. You'll see the channels, the routers, the transformers. You'll see the flow. You will understand how the data moves, how the work gets done, and how to make it better. This is the power of enterprise integration patterns. They are the blueprint for communication, the foundation for modern software architecture. The blueprint is now in your hands. Now go build something incredible.